Hello friends, in this lecture we are going to learn about generators. The idea of generator is used frequently under linear algebra and abstract algebra. But for now, let us learn this concept of generator in the vector space. Suppose my W is a subspace of a vector space V over R. Then we say that this subspace W is generated by a subset S of V if my W is the smallest subspace of V which contains S. Okay, so let's try to understand this concept. What we have is we have one subspace. From this subspace we are trying to find out a subset of V such that this subspace W is the smallest such subspace which contains that subset S. Correct? So from a subspace we are trying to find out a subset. In the last class where we were discussing a linear combination, we were trying to do something similar but in the reverse pattern. What we did is, in the last class we have given a non-empty subset S. From that non-empty subset we found out L of S, the linear combination of element of S, and we proved that that is a subspace. That means in the last class we discussed that from a subset we can find out a subspace. In this lecture, while defining a generator, what we are doing is we are just taking a subspace, and for this subspace we are trying to find out a subspace. So ultimately we are just going to connect both these ideas. For now, let us see how we write the term generators, means how we denote it. So suppose my W is generated by S, then we denote it by this. That means we write W is a span of S, or we use the notation of generator like this. This notation can be used, you can see in different reference books. Okay. So what we see is, given any non-empty subspace, if I want to say it is generated by S, then W must be the smallest subspace such that my W contains S. Means if I want to find out the generator, what I will do is I will just take a subset of V and will check, is my W the smallest subspace which contains S? If not, I will just change my S and find out some other subset which satisfies our property. Okay, so looking at this from the first side, we see that it is really difficult to find out the generator, but once we see example it will be really simple. And one more thing which we should note over here, the generator over here is not unique. There is a simple note that you should understand. Means if I want to find out a generator of given non-empty subspace, I might find out some another generator, you might find out some another generator, it is fine. There is no unique generator. Okay, so we know what the definition of it, and we know something, it is converse of a linear combination. Now what we do is we just try to connect them. That means what I am trying to do is, in the linear combination we learn that from the S we can find out LS, the subspace. From a subset we can find out the linear combination that is a subspace. Correct? Now we will connect these two things. That means we will show that my L of S is generated by S. That means we will show that my span of S is nothing but the linear combination of S. That means we will show L of S is the smallest subspace containing the set S. Okay. From the definition of LS, we know that L of S is a subspace and it contains S also. Right? So we know that L of S is a subspace which contains S. The thing to remain to prove is L of S is the smallest subspace. Right? So if I want to prove this is the smallest, that means what? I will consider any other subspace and I will prove that L of S is smaller than that subspace. Then I am done. Since there does not exist anything which is smaller than LS, my L of S is the smallest. Correct? So we consider, suppose my W is some subspace which contains S inside it. If W is a subspace which contains S inside it, my claim will be my L of S is smaller than the W. Correct? W is any subspace which contains S. My claim is L of S is a subset of W. That means my L of S is smaller than W. I want to prove L of S is a subset of W. That means I will consider any element of L of S and I will prove that is inside W. Suppose I consider X bar inside L of S. How does element of L of S look like? Where S has been the same set of the previous lecture. That means S contains K element V1 bar, V2 bar till Vk bar. Then the element of Ls will look like alpha 1 V1 bar plus alpha 2 V2 bar plus dot 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 plus alpha K Vk bar. So my X bar looking like that. My X bar is nothing but that element. Okay. My X bar is an element of Ls. I want to prove it should be inside W. What is W? We defined that W is nothing but a subspace containing S. If it contains S, that means it has all elements of S. That means my V1 bar, V2 bar till Vk bar, all are the elements of W, since they are inside S and S is inside W. Now, if these elements are inside W and W is a subspace, then it must be closed under the scalar bracket. That means I can say alpha 1 V1 bar, alpha 2 V2 bar, dot 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 alpha K Vk bar are also element of W. And if I add them, still it is inside W. The simple reason for both of this is my W is a subspace. So we just prove that my X bar is an element of W. Correct? So we prove L of S is a subset of W. Means we simply proved that L of S is the smallest subspace containing S. Hence, I can conclude now from the definition of the generator, my L of S is generated by S. Okay. The idea of a generator is difficult when you see it first time. But when we will see some simple examples, the idea will get clear for sure. For any doubt, please write in the comment. Like, share and subscribe to my channel. Thank you.